So I'm going to talk about the climate, carbon cycle, and photochemistry. So photochemistry, if I have time. So in fact, studying the climate on the early Earth give us some indication about the environmental condition in which life appeared and evolved. And so the temperature of the early ocean may have been critical for the processes leading to the appearance of life. And so these processes and the reaction would have been different with frozen oceans or warm oceans at like 60 degrees. Okay. In fact, there has been a long debate about the temperature of the early oceans, and there is still a debate that started with measurements of oxygen isotopes in oceanic charts, suggesting warm temperature, high temperature of 50 to 70 degrees Celsius. And this high temperature were also compatible with biological evolutionary models, so suggesting that the ancestra of life were thermophile during the Archean, living in temperature of 60 to 80 degrees Celsius. But more recent measurements using other isotopes suggested lower temperature, like below 40 degrees Celsius. And also we have indication of glacial rocks, like at 3.5 billion years. And also we have the Huronian glaciation that are difficultly compatible with these warm oceans. And concerning the previous modeling, 1D climate models by casting suggested that 2 to 8 bars of CO2 were required to get these warm oceans. And some work by Slip and Zanley, looking at the carbon cycle, they found that only cold climate could have occurred on the early Earth, with PCO2 between 1 and 5 millibars, and that during the late heavy bombardment, the weathering of ejecta would have produced very cold climates. So our goal was in fact to revisit the climates and the carbon cycle on the late Hadean and early Archean with updated models, in particular with the 3D GCM, to determine the condition for getting warm climates and also to look at the equilibrium points of the carbon cycle. So we use for the climates the generic LMDZ GCM. So that's a model we developed at the Laboratoire de Meteorologie Dynamique to simulate any kind of atmosphere. So François Forget will describe in more detail the model on Friday and all its applications, so I will be brief. Just it includes a 3D hydrodynamical core that is very general, a radiative transfer module that can work for any atmospheric composition, and also take into account the radiative effect of clouds. It includes turbulence, convection, conduction in the ground. We have a full water cycle that can work also for warm conditions and moist atmospheres, and also a two-layer dynamical ocean that simulates the heat transport and the formation of sea ice. And also recently we included a photochemical module that can allow to simulate hazes. I will describe that just at the end. Okay, so we applied this model previously to study the Feng-Chung-Sun paradox. So the fact that the solar luminosity was lower during the Archean, and that with the present-day atmosphere, the Earth would have fallen into a full snowball Earth, while we have indication of presence of life during all the Archean. So that means that there was warming processes allowing to avoid the glaciation. And so we tested all these warming processes and this hypothesis with the GCM to find at what condition we can get a temperate early Earth. And so we found that we can maintain equatorial water belt with quite low level of CO2 just by doubling the amount of CO2. And we also found that for a CO2 and methane-rich atmosphere, so we can get temperate climates with concentrations that are compatible with the geological constraint we have for this period. So now I will focus on the climate, the warm climates. So we did here simulation at 3.8 billion years, so as a transition between the Adian and the Archean. So we take into account the rotation period at that time, the lower luminosity, so 75% of the current luminosity. We assumed that there was no land, or only a very small fraction, and 1 bar of nitrogen. So you have on this figure the mean surface temperature for a PCO2 going from 10 to minus 2 bar to 1 bar. So in blue without methane, and in red with 2 millibar of methane. And you can see that with 1 bar of CO2 here, we can get high temperature of 60 to 70 degrees Celsius. On the right, so you have the zonal mean temperature profile as a function of latitude with no methane and for the different PCO2. And so for the warm climates, there is almost no temperature gradient between the equator and the pole. So compared to the previous 1D model, we found that with 2 to 3 times less CO2, we can get the warm ocean at 60 degrees. And the main reasons are the updated opacities in our model, also the fact that we consider a very small length fraction, while in the casting model they assume the present day length fraction. And also we found a cloud feedback in our model, a destabilizing cloud feedback that tends to increase the temperature for high PCO2. So the next question is that 1 bar of CO2 doesn't seem crazy, so it's to know if it is possible with the carbon cycle to get these warm oceans. And also, otherwise, to determine what are the equilibrium points of the carbon cycle. So for that, we use the outputs of the model, so the temperature, precipitation, and evaporations as a function of PCO2 and latitude, as input for a carbon cycle model developed at the Institut Physique de Globe de Paris. So it's a quite complex model that includes all the processes for the carbon cycle. So in particular, there are the flux from the mantle to the atmosphere and the ocean from mid-oceanic ridges and arc volcanoes. So we assume a classical plate tectonic regime. And also it includes the flux of the atmosphere and the ocean to the mantle by subduction and by the weathering of continents and also the seafloor weathering. So that is the dissolution of oceanic basalt by hydrothermal circulation and producing carbonates into the hydrothermal veins. So there are a lot of parametrization in this model, so I will be brief, just discussing a few of them. So for arc volcanoes, there is one part coming directly from the mantle and one part due to the recycling of the subducted carbon, with R the fraction of recycled carbon. So for the mid-oceanic ridges, we assume that the flux is proportional to the oceanic crust production rate, that is the seafloor weathering times the thickness of the crust. And we expect that this production rate was higher on the Archean Earth. And so for the continental weathering, so we take into account the temperature and precipitation. For the seafloor weathering, so we assume that it is proportional to the spreading rate, and contrary to the previous models, we take into account the feedback by the temperature, in particular by the deep ocean temperature. And this is necessary, this temperature feedback, to explain the higher concentration of carbonates in late Mesozoic oceanic crust that indicate a 5 times higher concentration of carbonates at a time where the climate was warmer. So we explored after different parameters for the early Earth, so with the length fraction from 0 to 26% of the present day fraction. We assume a production rate 11 times higher than today, and we tested with the present day oceanic crust thickness or a thicker crust of 18 kilometers. And we tested also with a recycling efficiency of 10% or 30%. So just I show you here the results assuming no land. So in that case, the carbon cycle is controlled by the seafloor raise ring, and you have here the mean surface temperature as a function of PCO2, so from the GCM in red and blue, and you have in light blue and in purple, so the intrinsic response of the carbon cycle model. So when we fix the sea surface temperature, and so the carbon cycle equilibrium points correspond to the crossing between these curves. And so we found that the temperature dependence of the seafloor raise ring is very strong and limit the possibility to get high temperatures. So after we explored for the different parameters like the recycling efficiency, the thickness of the crust, and the land fraction, so I will not describe detail all these different cases, but just for all cases, we found that the land cover has quite a small effect. All the carbon cycle is dominated by the seafloor raise ring, with the higher production rate at that time. And so we always found temperate climate, so with temperature between 8 and 30 degrees Celsius. So we found that the carbon cycle is very efficient to maintain temperate climates. So after we look at the climate during the late heavy bombardment, so we wanted to see the long-term effects of impact on the climate and on the carbon cycle. So we included the effect of ejecta due to the production, the effect of impact due to the production of ejecta that are easily weathered and so tend to decrease the PCO2. We included the outgassing of CO2 from impactors and from the vaporization of carbonates in the crust, and also the mass of impacts after impact. So we did some run assuming a stochastic sequence of impactors for the late heavy bombardment. I show here just the result for 10 million years of the LHB, and we consider either asteroids or comets, so with different impact velocities, and also we assumed for asteroid 1% of CO2 per mass, and 20% for comet. So it's quite a high value for comet, higher than one Hervé Cotin showed yesterday. But so you have here on this figure, so the cumulative CO2 that is consumed by ejecta in red and outgassed by the impactor and the crust in black. So in solid line for asteroid and dashed line for comet. And you can see so that the ejecta raise ring dominate so the effect. And so that has a dramatic effect on the climate and the PCO2. So you can see the evolution of the PCO2 during these 10 million years, and a very strong decrease of the PCO2 for different cases. So in yellow with asteroids, in red with a thicker oceanic crust, but also asteroids, and in blue with comets. So in all cases, we find a very strong effect of impacts, and potentially glaciations triggered by the largest impactors. And so finally, I will describe just briefly. So we included a photochemical model in our GCM. So for the first time, we can simulate in 3D the photochemistry on the early Earth. And so there are many possible applications of this model, and we start using it to study the formation of organic hazes on the early Earth, in the case of a Titan-like early Earth. So we have indication for a possible Mason-rich atmosphere during the late Archean, with episodic formation of hazes. And these hazes could have triggered glaciation by anti-greenhouse effects, explaining, for instance, the glaciation at 2.9 billion years. And they could also have produced a UV shield, so protecting life, and also allowing to accumulate some molecules that are otherwise photolyzed in the atmosphere, like ammonia. And so the previous Wendy model showed a very strong effect of these hazes. So you have here the mean surface temperature with the Wendy model as a function of the percentage of Mason. And organic hazes appears when the ratio of Mason and CO2 is 1.2. and that produces a strong cooling of around 20 degrees Celsius. But so it may be habitable, but so we need a 3D GCM to test that. And so we are testing the production and the dynamics of hazes with the model. So we included a network of reactions with a pathway to the formation of hazes. And so we can start to see already the effect of the atmospheric circulation leading to a transport of hazes to poles. You have here the column of hazes as a function of latitude, and we see a transport to poles and a minimum at the equator. So that could allow a lower anti-greenhouse effect, and so that could have some big impact on the climate. And so the next step is to include the microphysics and look at the relative effect of hazes and to study after the dynamics and the climatic effect. And that's my summary, and thank you.